Generalization and simplicity. When we generalize a result, we make it more useful. It may strike you as strange that a generalization nearly always makes the result simpler too. Wow. The more powerful result is easier to learn than the less powerful one. This may be illustrated by means of the very trivial puzzle, which runs as follows. One glass contains 10 spoonfuls of water. Another glass contains 10 spoonfuls of wine. A spoonful of the water is taken from the first glass, but into the second glass, and mixture is slowly stirred up. A spoonful of this mixture is then transferred to the first glass. Will the amount of the wine in the first glass at the end of this procedure be more or less than the amount of water in the second glass? The obvious way to go about this question involves the following calculations. After a spoonful of water has been put into the wine, the second glass contains 10 spoonfuls of wine and 1 of the water, 11 spoonfuls in all. 1 spoonful of this mixture will therefore contain 10 divided by 11 spoonfuls of the wine, 1 divided by 11 of a spoonful of water. After transferring its first glass will contain the 9 times 1 over 11 spoonful of water, 10 over 11 spoonful of wine. The second glass will contain 10 over 11 spoonful of water, 9 times 1 over 11 spoonful of wine. The amount of wine in the first glass is therefore exactly the same as the amount of water in the second glass. This being exactly the same might be an accident, but if you vary the condition of the problem, you will find you always get equal amounts. If we begin with x teaspoons of the water and x teaspoonfuls of the wine, the amount of wine that gets into the water still equals the amount of the water that gets into the wine. Even if we make the glasses begin with unequal amounts, if we put x teaspoonfuls of the water in the one and 1 teaspoon of the wine in the other, and then follow the rest of the instructions as in the original problem, our calculations still show that at the end of the water in the first glass is equal in amount to the wine in the second glass. Now, this is a clear example of bad mathematical style. In the good proof, an illuminating proof, the result does not appear as a surprise in the last line. You can see it coming all the way. This particular puzzle used a kind of the camouflage. It tells you something which you do not need to know, and by so doing distracts your attention from the real point. Then the unnecessary statement is that the mixture is slowly stirred up. The essential point is that we transfer 1 teaspoonful of the liquid from the first glass to the second. And then we bring back 1 teaspoon of the liquid from the second to the first. It does not in the last matter what kind of liquid. All that matters is that at the end, each glass contains the same amount of liquid that is did at the beginning. If this is so, the first glass must have received just enough wine to compensate for water that it has lost. And of course, the water it has lost will be found in the second glass. The amounts cannot fail to be equal. No fractions, no algebra need be employed. Really? The general statement of the puzzle would therefore be: we have a glass of water and a glass of wine. We carry out any series of operations with these liquids such that the total amount of the liquid in each glass is the end what it was at the beginning. Then the amount of water that has got into the wine must equal the amount of wine that has got into the water. But this is so obvious that it is hardly worth saying. It is much simpler than the calculations we had to do earlier. but the range of the puzzle to which it applies is far greater. You could switch teaspoonful of the liquid backwards and forwards between the two glasses as many times as you liked, and the principle would still apply. The investigation of the problem therefore consists of the scraping away all unwanted information until only the essential facts remain. The less you are told, the easier it is to find a solution. A general theorem rarely says anything complicated. What it does is to draw your attention to the important facts. In elementary mathematics, we have a bocce of the details. In higher mathematics, we attempt to isolate the various elements involved and to study each by itself. Higher mathematics can be much simpler than elementary mathematics. Yes. Perhaps the most famous example of the simplification by generalization is Hilbert's finite basis theorem. In 1868, Gordon had proved by laborious calculations and certain theorem which I will not here attempt to state. It aimed at showing that a certain collection of the polynomials which had arisen in a connection with a particular theory had a certain property. In 1890, Hilbert proved the result very simply and without calculation. The advance was due to his throwing away 90% of the information used by Gordon. Wow! He proved the result to hold not merely for those particular collections of the polynomials, but for any collection of the polynomials whatever. Wow! We have gone from the ridiculous to the sublime. Nothing could be more trivial and localized than the wine and water problem. Nothing more profound and far-reaching than Hilbert's theorem. The fact that both can be covered by the same maximum, greater generality and greater simplicity go hand in hand is perhaps an example of the power of mathematics statements to bring widely separated objects under the same proof. Yes. One cannot judge the importance of any mathematical investigation by the particular object it discussed. Topology is an example. Topology is sometimes referred to as the rubber geometry, the geometry of the figure drawn on the elastic sheet, and so in a way it does treat all the properties of such figures, but its importance derives from the fact that on a rubber sheet there are no fixed lengths. There cannot be any result like a Pythagoras theorem. We can only make remarks such as this curve is continuous, that one is broken into two separate parts. Continuity is a basic property in the topology, and topology has something to say about anything which is capable of varying gradually. Wow. As there are very few things incapable of such a variation, topology has a very wide influence. It is increasingly becoming the concern both of the pure mathematicians and of the technicians. Some most remarkable results can be proved by it. It has the utmost generality and the utmost simplicity. Wow! Woo!